you are presenting some of your NSF Critical Zone Collaborative Networks Dustḳ2 results at EGU 23 in Vienna. You have one of the 3-minute slot, I believe is how long you get.
Two
Two
minutes.
minutes. I keep trying to give you a little bit more. You got 120 seconds to give people an overview to get them in. So today I was going to ask you about some specifics that are in sort of abstract description of
Great.
your part of the session, because I'm curious to learn a little bit more of those very specifics. So I had downloaded the PDF. I'm going to open it and look at it and ask you some things about it, if you're comfortable with that.
Super. Someone read my abstract. This is
I sure
wonderful.
did. I did. So one of the things it says in here is the expanding human populations and widespread disturbance due to land use, dust deposition, rates and compositions are changing. Can you talk a little bit about this widespread disturbance due to land use? We're becoming more and more familiar with what humans are doing in the critical zone, but you're specifically talking about it in Vienna.
Absolutely. And I think this is one of the things that helps illuminate why the Dustḳ2 project is, I think, so exciting and multifaceted, is that we're not solely looking at dust deposition or properties of dust. That might be something that I personally focus on, but part of our team is also working on why is dust coming off the ground in certain parts of the world, particularly in our case in the southwestern US, and is that changing over time? And indeed, it is changing over time, and it's mostly driven by a combination of climate change and human activity, whether that's developing formerly pristine landscapes for new roads, expanding cities, mining, ranching, things that have a footprint on the landscape, that we just need to be careful about how we're doing and how widespread that footprint is. And keeping an eye on the fact that these are also environments that are currently threatened by drought and by a rapidly changing climate system.
This for me is so fascinating because this is where the bridge between the research and the writing leads into policy making. The more that you know how this land use affects the movement of dust, the more when they're considering developing areas or granting new resource development licenses, that the findings that your team is pulling out can really inform, is that a good choice to make? Is that going to be harmful? Is that in the safest way that we can? You're not saying to stop any of these things.
Absolutely. I mean, we're doing the science to try to inform better decision making. I mean, the best way to put it. And I feel like particularly in northern Utah, with the situation surrounding the Great Salt Lake, that our team has really done a good job of that. So team members like Kevin Perry, for instance, at the University of Utah, is in the news quite frequently as someone that different organizations want to talk to for his take on the Great Salt Lake and what's going on there. And therefore, Kevin and other team members are, invited to contribute to guidance documents and visits to the State House there in Utah to talk about what lawmakers should know as they design policy going forward.
And Mackenzie Giles and her team also does a lot
Sure.
of land use with recreational stuff.
Yep.
The skiing is such an important part of the economy in that part of the world.
Absolutely.
And this land use has a direct impact on that. We're going to keep on going through. There's so much in the abstract to unpack. I'm going to just hit a couple of highlights as we talk here today. One of the things that you say in here is a massive increase in dust deposition rates in the past century. A massive. That is a powerful, strong word to use. Why did you choose the word massive?
Well, not my work, but work that people have done has really conclusively demonstrated that there was a, shall we say, massive or dramatic or abrupt or significant increase in the rate of dust deposition in mountain settings, particularly where those early studies were done in southwestern Colorado. It's abundantly clear looking at lake sediments that are slowly, receiving dust, which is landing in the watershed over time. And you can core down into the bottom of a lake and you can pull out sediment that goes back in time before European settlement, certainly. And you can calculate what the average rate of dust deposition was over time. And then in the late 1800s, so a little more than a century ago, you see that rate increase, I would say massively, several 100%. So
And does that rate continue to go up, or has it sort of stabilized now, or is it just, does it get more and more and more?
that's an excellent question. It seems like it was more of a step change where things jumped into a new mode rather than just kind of shooting for the sky and continuing to climb ever higher. But was something we need to keep an eye on. Certainly, we need to have studies which are constantly looking for changes in rates of dust deposition in order to answer that exact question.
This is a highlight of the importance of long-term research. You're looking back at, fortunately, you have the sediment cores that
Right.
should take you back in time, but you've also spent more than a decade and a half of collecting and looking and studying some of these things, so you can really look at the time in one specific space. Talk a little about why that's important to you as a researcher.
Well, I think you always want to have the context for whatever your research question is, and in many cases a lot of that context is time. Is it's a temporal context. How is my observation today compare with if I had made this observation yesterday or 2 years ago? Or speaking like an earth scientist, what if I had been able to do this 1,000 years ago? How would the situation have been different? So when you invert that and you look forward, you can see the value in maintaining these operations that are building slowly, incrementally building these long-term data sets. They're going to be of value now, but they're going to be of value in unknown ways in the future. I think that was a real strength of what NSF was looking for when they considered the construction of this critical zone thematic network, which is of course much larger than just our Dustń2 project. They were particularly looking in part for projects that could take advantage of existing infrastructure, existing data, existing mechanisms for collecting long-term data sets, recognizing that those are just so valuable. Why stop? And conversely, why start something new if continuing something which has yielded good results could continue to yield results into the future?
I've been in sessions where critical zone researchers have said, we have this data set from the 50s and the 60s that was at this site. It had information in there they weren't even thinking about when they were
Right.
collecting it, but it's so helpful to us now. And
Yeah.
we're really grateful for the work that we did. So some of the stuff that who knows what the way they'll be studying the stable isotopes that you're collecting, all that sort of stuff, what it will mean for the future.
Absolutely.
I want to ask a little bit about, you talked about looking to the past with some of these long-term data sets. I'm assuming that that information could also be used to make models for modeling what could happen in the future.
It can be used to make models, and it can be used as input into existing models, or it can be used as linkages that connect existing but currently separate models. It's very exciting, and it's a very dynamic component of science in general now, and particularly critical zone science. From the perspective of our group, we have models which are involved in answering the question, why is dust emitted from one particular point in the landscape but not another? We have models about how does dust get from point A to point B, as you would imagine, transport models. There are models that are, okay, if you put this much dust with this particular properties onto a snowpack that's this deep, how much more rapidly is that snowpack going to melt because of the addition of that dust? There are models about what the delivery of dust with certain nutrients in it is going to do to the functioning of alpine, terrestrial, and aquatic ecosystems. And so you could imagine the ever increasing scale of trying to knit these together, both to understand what's happening now to a better degree than we currently can, but also to use in a predictive framework looking forward.
There's a little bit of a side, but I'm going to ask you, are you excited about some of the possibilities of artificial intelligence and machine learning that can help inform these models' effectiveness and
I
accuracy?
think, yeah, it's a great question. It's I don't know if excited is the right word. I'm intrigued, curious, slightly apprehensive, I suppose. If anyone paying attention to the developments just in the last half a year basically has to be amazed with how rapidly this is coming out, and things that not long ago we would have thought were still deep in the future, or at least a few years into the future, and now you could be asking Chat GPT these questions and see what kind of answers you get, and maybe some of them would be good and some of them would be less good. But that would have just been a funny idea 6 months ago, and now you can actually go do that.
And your students may be doing that right now.
Try not to think about it, but anything's possible. Yes.
So you'll be able to look at some of these other, and this long-term research and long-term data sets help track more massive changes into the future.
Good word choice.
Thank that was it was one of the things that you mentioned is the network of 18 passive dust traps you use, which is another fun word to use, trapping that dust in there. Does dust try to escape from the traps sometimes?
Oh, I'm sure it does, but we try to hinder that.
So it's 18 now. It's a growing network of the passive collectors that you have out there. Talk a little bit about the growth of this network, and where was Dust 1 and now you have Dust 18.
Right.
Could you have even imagined as you were replacing Dust 1 that you would have Dust 18?
I could easily answer that as no. I put the first four collectors of my design out in 2011, so 12 years ago this summer. And at the time, my objectives were fairly simple, elementary. Like, is there dust landing in this environment? If so, how much is it coming in at different times of year? Things like that. Real elementary starting points. It yielded really interesting results that I was fortunately able to, use as leverage for obtaining funding to expand that network, thanks to the support from NSF. And then now, a decade later, I have actually have 20 of them now. You haven't even met Dust 19 or Dust 20
Whoa!
yet. I'll save that for another day. But I have 20, and of course, that's just part of what Dustquared is doing. My colleagues have dust samplers really of different designs appropriate for their individual research questions at locations throughout the Midwest and the Rockies and the Southwestern US. It's really kind of amazing.
You mentioned some of that in this abstract. I believe you talk about the different levels of dust that come in. I think right here, lower fluxes are common at high elevation sites in Nevada. And before that, you say higher values at the urban sampler in Salt Lake City.
Yeah.
Is that surprising results, or is it that you expected, or do you try to say, we don't know, we're going to just try to keep an open mind and find out what we're going to find out?
I find it's always a balance between just going and trying to find things out, and yet also having a hypothesis, having a plan, having a rationale for what you're going to test and why and how. Um, for instance, deploying a sampler in an urban setting like Salt Lake City, and there's a few others now, that seemed like an obvious thing to do. Are these values that we're getting, high elevation and essentially pristine mountain environments? How representative are they of different parts of this broader landscape that don't all look like high, pristine mountaintops? And so it wasn't a surprise personally that the value in Salt Lake City, for instance, was higher than in some other places. But surprise comes in different scales or different flavors. Like, I was quite surprised that some high elevation sites had fairly low values, and I'm still trying to figure out why.
It's that dust, it's escaping the traps. That's what's going on. They
You're
know you're
making me
coming,
think.
and they know.
You're making me think. That's right.
One of the things that you mentioned here is with the lower fluxes at high elevations, particularly during the winter. Is it How does the weather, not the climate, but the weather
Yeah.
affect some of the dust movement? Is it because it's colder, or is there less wind, or less? What do you think it might be?
Yeah, well, the answer that I would give you, it depends on the time scale, which sounds like a great earth science type answer. But this is
Right.
another strength, I would argue, for the way our Dustquared project is running, is that we're all interested in different and complementary timescales. So someone like Mackenzie Skiles, who's looking at a layer of dust that accumulated in the snow in 3 hours in one afternoon, and maybe what that does for the snow melt over the course of a couple of weeks, that's a really short time scale. It's a very relevant time scale for those processes, but it's short. And I'm interested in, what does dust deposition do if it occurs over 100,000 years? How does that affect the properties of the soil, which doesn't form in 3 hours? A soil forms over thousands and thousands of years. So looking at those seasonal differences may be a point of overlap. It's maybe a point of overlap. In my work alone, can't answer those questions about why the seasons might be different or one year might be different. But it can contribute to that, I hope.
The last little bit, and this is the literal last sentence of the abstract, the grain size distribution, color, mineralogy, and geochemistry of dust also vary notably between sites, supporting the interpretation that much of the dust is sourced from the immediately surrounding lowlands. That sounds pretty close to like, this is an actual conclusion that we are able to draw rather than more work is necessary, which I
Yeah.
often find at the end of scientific writing. Is this a real conclusion?
I would say that's my, what did I said, interpretation,
Yes,
conclusion.
interpretation.
All right, it's essentially a conclusion from this 1 year of data. How's that?
Okay, that's fair. That's
What
fair.
I'm primarily focusing on in this talk in Vienna next week is what I see from the first year that this full network of 18 dust traps or dust collectors was in operation. And it was the first time that we really had data to get at questions like how variable is dust composition or is dust deposition rate over larger areas, from one state to another and things like that, using the same design, using the same field protocol, keeping sampler deployment positions essentially the same, trying to hold things constant. And I was really surprised at how different the dust was. At the end of the day, that was what jumped out at me. And I would simply say that you could imagine two end member scenarios. One is that the dust arriving in these samplers is this really well mixed, probably really far traveled, homogeneous material that is not different in southern Idaho or in eastern Nevada or in southern Utah because it's come from thousands of miles away. It's been so well mixed, it's uniform. Or you could have notable, did I say, or maybe even massive differences in the properties of the dust between these sites, which are not quite compatible with the idea that the dust in this situation is uniform and is wide traveled. And I'm only looking at a particular part of the dust. I'm not looking at every possible imaginable characteristic of the dust. But what I found is that it varies a lot from place to place, which I think is best explained with the interpretation that it is coming primarily from relatively nearby locations in this setting. That's by no means meant to say that that applies everywhere, but in the locations I'm working on, that's what I think I got from this first year.
And the things that I've been learning about the movement of dust throughout the planet, there is a lot of idea that something gets blown up in the Sahara, comes over the Atlantic, and then it lands, and then, oh my God, the dust on my car, that came from Africa. So
Right.
you're not discounting that, but it could be more likely that the dust on your car came from your garden in the backyard.
It depends on your scale, certainly your time scale and your spatial scale. And I'm definitely not discounting that. I'm sure that in the background of all of my dust samples, there is some component that is consistent, some component that is this hypothesized, homogeneous, uniform, far traveled material. I think it's overprinted, though, at least in the way I'm sampling and in the locations where I am sampling. I think it's overprinted or kind of masked by more regional material that is probably blowing up from arid landscapes not too far away below the dust collector.
That is fascinating to think about. And that is really new ideas and new things that you'll be presenting to your fellow researchers and scientists in Vienna.
I look forward to getting their feedback on it and getting their take. And I also, of course, look forward to seeing how this interpretation holds as the project goes forward and we have a few more years of data to test.
One more little thing about that is if it turns out that some of this notable interpretation is incorrect in the future, would your feelings be hurt? Or would you be like, oh my gosh, great, thank you so much. I'd love to learn more.
I don't think my feelings would be hurt. I think it's the process. I would lean toward your latter option. It would be exciting to see. It's always exciting to see what you get next in any project.
What's the first thing you're going to do at EGU? Because you get your badge, you get your lanyard, you're going to go in there. What are you going to do first?
Get the lay of the land. I actually am going to go to so this is my plan. less than 24 hours after arriving early on Monday morning. There's a session that I want to attend. And so we're going to see if I can fight back the jet lag by hustling over to the convention center and getting to work. But it's going to be a very, very exciting week from Friday morning or Monday morning through Friday afternoon.
Just adrenaline keeps you going, the excitement of discovering, learning,
I
reconnecting,
love
network.
conferences. Yeah, I love big conferences, and yeah, reconnecting, networking, new people, old colleagues, former students that are going to be there presenting on the work they're doing in graduate school. That's always a wonderful, wonderful feeling. So it's going to be fun.
My last question today. The last time we talked about some tips for what to do.
Ah,
What would you say to not do? What seems so tempting, but you would say, I've tried that, and trust me, that's not the best way to go. Go to EGU.
oh boy, this is certainly not EGU specific, but I think there's can be a tendency when planning out, a course of action for a morning is to think, okay, I'm going to watch this talk in this session, and I'm going to run to the session over here and see this talk. And there's a time and place for that, particularly if it's students or dear colleagues that are giving these talks that you really want to be present for. But if you run all over the place, you're going to inevitably miss a lot of stuff. So it might be worth just buckling down and saying, every talk in this session's got something to tell me, and I'm gonna ride it out from start to finish. That can be quite rewarding.